Okay, a student sent me a question about Atwood's machine. So we're going to look at the analysis that they did. So this is the file that they sent me. First of all, apology, aphasia. Been having a problem with that. So sometimes my words don't make any sense, but I'll try to do my best. All right, first of all, let's investigate. They had a concern about specifically the chart. They said their theory line and their data line looked a little bit off from one another, and I agree. I've also noticed something curious over here. There seems to be two y-axes and then an acceleration axis. So things aren't exactly the way we'd expect them to be. So let's investigate the data. Let's start by looking at the masses, and these look acceptable. Total mass. Well, here we would really expect to see a sum equals this mass plus this mass. Okay, a mathematical sum, and I'm sure it's the same thing. Let's just drag this down one by one and see if the values stay the same. And indeed, we were supposed to see the same value except for uncertainties. So let's just keep dragging this down. There's a little bit of variance right here. That's okay. So we have a total mass that was supposed to stay the same because the idea was they were taking one washer from this mass and putting it over on this mass to create run 2. And then again, moving a washer from here to here. It was a small 5-gram mass or so. And with each run, they were simply shifting a washer from one side to the other, increasing the difference in the mass. But the total mass should stay the same. Now, it doesn't appear to stay exactly the same, and I kind of appreciate that because there should be uncertainties here. This mass is not, we don't know that exactly, right? There's some uncertainties here. Likewise with mass 2. And so when we add them up, that uncertainty, let's say it's a 1/10 of a gram right here and 1/10 of a gram here, we could see some fluctuations here in these numbers. And in fact, here we see that 1/10 of a gram difference here, and here it's a little bigger, so maybe a wrong value was recorded, but that's okay. Now right here we wanted to see instead of a number, so I can see that these students did not learn to or do not appreciate the idea of using formulas. So I'm going to type equals average and then highlight total mass from the first value to the last value. And that writes this reference for me. And then I can close the parentheses and just hit return. And see, I get the same number, so I know they calculated things properly. But it kind of helps. And by the way, I'm increasing the decimal places right here so that I can see one more decimal place. See that there's a slight variation. Now right here it says the uncertainty in mass. So I'm going to do equals STDEV, open parentheses, and highlight the exact same values again for total mass. Be careful not to highlight the accelerations because these are not the same numbers. We don't expect that. Instead, this average right here, these were supposed to be the similar numbers, so we're going to find out how different they are. The standard deviations should tell us how big a difference between all these. And it looks like, oh, that's pretty cool. It's 2 grams. Let's increase the decimal place 1. Okay, so we have 1.7 gram uncertainty. And normally we just, in this lab, we just want to show one significant figure for the uncertainty. It tells us to what decimal place we know this number, and at that decimal place, how can we count? And so now I can reduce this to match decimal places with my uncertainty. Now, the acceleration should have just been a value inputted from Data Studio. It was velocity versus time, the slope. The applied force, we should have the difference in masses, difference in B2 and C2 times G, 9.8. That looks good. So they do know how to do formulas, and they filled those down, and we have all those same numbers. Newton 2 applied force. So here we have B12 plus D12. I think we just found their mistake. because we wanted to take this equation should be the total mass times acceleration. But we're going to even be more careful than that. The reason we want it a lot more carefully because the total mass, remember, is changing a little bit because of uncertainties. And Newton 2 force is supposed to be, this was supposed to be a theory, okay? This value right here. So we want to make sure that our slope is constant, all right? So we're going to use this value right here for the slope instead of the individual total masses, because these values are changing, which would no longer allow this data to appear perfectly linear. Instead, it would have some scatter, as we expect our applied force to have. So we're going to take the Newton 2 equation and rewrite this. Equals the average total mass, but here I want to be careful. Watch this. I want to put in a dollar sign right here, because when I fill this equation down, I always want to look at D20. And then I'm going to multiply by the acceleration. Hit return, and look, these numbers are a lot closer than last time. We can see that there's going to be a vertical shift in the real data. But this theoretical data set, see, now we're tracking. The numbers previously were quite a bit different off. And so we found the problem, and that was creating that plot. And in fact, if we go back to their chart, well, I'm not sure what's happening there because it didn't update. So we'll just create a new plot. All right, but before we create that plot, let's scroll down here and see how we're doing. We want to compare the slope, which we can say equals slope, open parentheses, and we choose the y values first. See right here it says give the known y's, then comma, and the known x's. So my known y's are up here. We have applied force, and just go to there, not to the blank there, and comma, and then the x's are right here. And then we can close parentheses and hit return. So now we have way too many significant, way too many significant figures. So I'm going to reduce those up here. Bada bing, 3 sig figs. And in fact, let's use the formatting palette, format, and copy this so we get the right units. There we go. And then we'll take off the color, because that green color specifically meant average system mass. And here we have the slope from the graph, which is a little bit bigger, but that's okay. And here, again, we use formulas, because if we change values, then things don't update. So we're going to take this number minus this one. And the one we expected was the average mass from the balance, because we know that's pretty true, right? We measured these things, and it wasn't too hard to measure them, so we kind of trust this number. Something's going on with the slope, so we're going to divide by our expected value of 219 grams. And this cell is already formatted as a percent, which means it's going to multiply by 100 and give us a percentage sign. Okay, and the vertical intercept is simply from the plot, which we haven't plotted yet, but we can just find it this way. Intercept, pardon me, I have a little bit of a cold here, and we do the same thing, the known y's, and then comma, and the known x's, and then close the parentheses, and there we go. Okay, so a little bit of an intercept. It means there's some friction in the system, which we know this value should be equal to twice the friction in one pulley. Now let's go down here and look at the accelerations, because the last trials, they dropped 5 times. They did a good job, and oh, there's different acceleration values. They found the average here, but again, they didn't a formula, so average, equals average. If I select it in the list, then it gives me the parentheses, and I just have to highlight and hit return. Now the standard deviation, it looks like they did this one properly. Standard deviation of those cells. But again, we're showing way too many sig figs. The idea with standard deviation for this lab is we're just going to look at one significant figure, because it tells us to what decimal place we can measure the acceleration. And so I'm going to reduce the sig figs and the acceleration to match. Now, we're also missing some units here, so we're going to insert some cells and just give ourselves some meters per second, okay, because that is the unit indeed of this data. So probably like that. Okay, so that describes all these values. And then just for the fun of it, let's go down here and say equals the uncertainty divided by 2.75. I said equals, I'm sorry. I meant to say divided by. Don't know why I did that. So there's our relative uncertainty, and we can just turn it into a percentage and add some decimal places here. So a 0.4% uncertainty. So we could state this number as 2.75, command option, no, shift option, plus or minus, shift option plus or minus, 0.01 meters per second. That's the statement of our acceleration. Or we could write 2.75, option shift plus, that's next to the delete key, the plus equals, and then we'll say 0. Well, actually, here I want to say meters per second, option shift plus 0.4%. These are saying the same thing. Okay, we're stating the acceleration and the uncertainty as a measurement or a relative uncertainty. Okay, so I know we're covering a lot, but let's go on to the plot. We want to plot acceleration on the x and free body on the y and Newton 2 also on the y. So I'm going to start up here and highlight all three columns down to the zeros. That null value is going to help us create a trend line that goes backwards. Pardon me for one moment. Yeah, aren't you glad this is a movie? I'm not sitting there in front of you. So let's go ahead and plot these. In this version of Excel, there's a chart menu right here. And I'm going to go into, well, those knuckleheads. They moved it on me. We want to look for scatter. Scatter. There it is in this whole list. Scatter. And then I right click and I say move the chart. Move it to a new sheet. Call it chart 2. That's fine. So inventive here. This right here, we actually want to format it as a line because it's the Newton 2 force, and we made it to be perfectly linear. If we had not made it perfectly linear, meaning we had used the total mass instead of the average total mass, we'd actually have a true scatter. But since we use the average total mass, we can actually use the scatter. So I'm going to go back into here, into scatter, and choose smooth line, and it's perfectly straight because the data was linear exactly. We're going to right click on the real data for free body applied force and choose add trend line, and in the options we're going to turn on display equation and display r squared value, the last two check boxes. And then we'll see our slope and our intercept. And those values, if you look at them carefully, they match the values that we got over here when we typed in those equations, the slope and the intercept. Okay. Now, to work further on this graph, we're going to go into chart layout, and then the earlier version of Excel, an older version, it's actually in a tool menu up here that you get these axes. So x-axis, we're going to call this what? This was supposed to be the acceleration measured in meters per second. Okay. And then we could add a y-axis title, vertical axis, and we could call this what? I'd call it just force in newtons. Okay, because there's two forces. There's applied force, and then there's Newton 2 force. Newton 2 is the theory, and applied force is the data. There's a few ways to get a text box on here. We'd like to go up here and say insert text box, but that's not available. For some reason, they left that out in this version of Excel. Silly people. One way is to go into the media options, and we want to go into shapes. And here's a shape that we could choose. Yeah, Command Z, undo that. Okay, it wasn't done loading. So I click once like that, and then I draw that shape. And now I can type in it. Believe it or not, I can just start typing. See, it doesn't give me a cursor, so I know that's a really strange way to do this. But free body applied force is equal to rectangle 1. Get out of here. Leave me alone. There we go. Is equal to, and now we'd want to put in the slope with units. Basically, write our two equations. One of them is free body applied force. We're translating this equation. And the second equation will be describing this line, which has a 0 intercept. And the slope for the red line here is equal to the slope that we programmed in, the total mass average. Okay, so what's missing still is two equations that are properly talking about these two lines. And then I think we're okay. Uh-oh, sample data is not here. We're supposed to have some sample data from Data Studio. So let's go back to Data Studio. I guess we haven't been there yet. I'm going to clear all the data and bring in just one of these runs. And my data had some goofiness down here. The start condition wasn't just right. So I'm going to highlight this data right here and say fit linear. And it gives me a value. So then I can go up here to edit, copy, and then go back to my, oh, by the way, we'd probably want to format this to make it look all nice. So we're going to drag it down here. We don't need to see that goofy data below. Just size it up so it looks good. And then we'll do edit, copy. And then back in Excel, we can do paste. Oops, I forgot. Pasting just gives us the data. Right here it reminds me, edit, paste, special. Edit, paste, special. And a picture. And so there's my picture. And now I can go up and say insert a text box. So that's what should be on the graph. But it's not available. And then I can just describe this. I want to answer 3 things. Okay, 3 things. Let's zoom in a little bit here. I want to say, what do I want to say? What is being plotted? 2, from whence did this data come? And then we want to say to, what's the third question we want? How did we use this data? Okay, so we'd want to annotate answering these 3 questions. And that's just one sample for the whole experiment. And so, of course, the slope of velocity versus time is the acceleration that this data came from, the smart pulley, and we're using it in the data table as the acceleration for trial 1, which doesn't match because this was actually my data at 0.146, and these students got something entirely different, which is okay. They just had different data than I'd have. Okay, so I hope that helps you guys a little bit. Finally, you need some proper units here, and fix this to say average mass instead of m2 plus m1. Use the average total mass times acceleration. Atwood's machine, in a nutshell, a rather large nutshell.